So good morning, everybody. It's the first time I'm in this seminar. Actually, I've been here many times, but unfortunately this is not the first time. Had I known that there are this type of a breakfast, perhaps I should a little bit reschedule and also. So first I have to say that, perhaps I introduce a bit more myself. So I'm at the moment leading the Earth Observation Research Unit at the house right next to this one, so the Finnish Meteorological Institute. And I have a background in atmospheric remote sensing. I've been working on atmospheric remote sensing topics since I started to do my master's degree. I was at that time at the maths department at the University of Helsinki. And since the beginning of the year, FMI, Finnish Meteorological Institute, we have also been part of the Academy of Finland Center of Excellence in Inverse Modeling and Imaging. So I will talk mainly about satellite data. So there is not really any machine learning here in the presentation, but there are perhaps, I tried to put a little bit ideas where it could be used, but these must say might be very naive. So, but I will anyway show quickly thoughts that came to my mind related to satellite data and machine learning, or what I know about machine learning, which is quite primitive. But I actually hope that there are many of you who might think that this could be an area where you could develop methods and utilize the data and develop solutions or efficient methods. I'm actually quite happy that there are so many people in this seminar. So great, let's go. So I will quickly start by introducing a little bit of satellites and in particular the Copernicus program. Then I say something about the measurement themselves, what are satellite observations, what are their characteristics, and then I show a few examples of air quality applications. So these are just basically images what I will show, just in some sense perhaps to give an idea which direction methods could be developed. And then I say at the end just what ideas related to what I think is the most potential field in using satellite data in the data fusion world. First I perhaps ask, how much time do I have?
About half an hour.
Half an hour, cool. Okay. So I start with the Copernicus program, and perhaps I go then quickly to this one slide, which is meant to be here for the motivation. So we are living in a world which is changing a lot due to the anthropogenic emissions, carbon dioxide in particular, that is emitted to the atmosphere due to burning of fossil fuels. You have all read the news recently, and the changes world is feeling at the moment. So there are areas where there is a lot of dryness, lack of rain, areas where there is too much rain, flooding, biomass burning is increasing in certain areas. So there are a lot of changes. Each place in the world is experiencing the climate change in a different way. So there is a lot of needs to understand what's going on in order to somehow adapt or mitigate the changing climate. The water cycle is changing, carbon cycle is changing. It affects on all fields, on humans, animals, vegetation, oceans, everything. And on top of that, there is of course then the human activity, all types of pollution that we have put into the air and the water. And all of these, they require really observations, global observations, to be able to understand better what is going on. And in this area, of course, the satellites come to the picture. So with satellites, we can get global observations from everywhere on the world, regardless of how difficult those places is to obtain ground-based observations. With satellites, we can cover all areas, all geographical regions, also politically unstable places, or even North Korea, we can observe satellites equally as the other places in the world. So the satellites there are increasing number of satellites, also for the environmental monitoring. So they all started with the meteorological observations. Now the weather forecast is really heavily depending on satellite data, but now also more and more environmental observations. So all types of other things that are monitored by the satellites. And in this picture I highlight a few of them. So this is an Envisat satellite, which was the largest environmental satellite. It was a European Space Agency satellite which worked for 10 years from 2002 to 2012. And then there is a very interesting NASA-led constellation of satellites on the same orbit. This is an A-train orbit, so every afternoon, 1:30 roughly, it goes over us also and observes our environment, atmosphere in particular, with a set of 5-6 satellites. They are flying in the same constellation, same orbit, about 10 to 15 minutes from each other. So together there is a huge amount of data that will be combined and analyzed together. I point out a few satellites. So here is a recently launched OCO2 satellite, which is measuring carbon dioxide in the atmosphere. So the most important anthropogenic greenhouse gas. And then I want to point out this one. Aura satellite, it was launched in 2004, and on board the Aura satellite there is a homing instrument which was built in the Netherlands and in Finland. And at that time we have worked a lot with the homing instrument. It's for atmospheric composition, ozone and air quality observations. And then there are other satellites. This is the latest air quality satellite, tropomic, also called Sentinel V precursor. But then I go now to the huge program that is being built in Europe at the moment. So all of the previous, like the Envisat and the A-train, they were more like research satellites. They provided regularly data, daily data even, and in a quite operational fashion. But the European Union is now leading us something in totally different level, I think, in the way of operations. So there is a program called Copernicus. Now I really want to know how many of you have heard about Copernicus. So like half. It's a huge program built now in Europe with operational satellites, and the image is not very good. So it contains satellites which are operated by European Space Agency and EUMETSAT, the meteorological satellite organization. They are built by European Space Agency, and then there are on top of the satellite data there is several services that are developed, operational services, meaning that the data is coming all the time, every day, very, very strong operational fashion. And then there is also an in situ component. The slide is really bad, which is then supporting the whole system. And the idea there is to provide free and open data to everybody, all fields of the society. I mean, it is aimed for European governments, citizens, industry, etc., scientists in Europe, but of course the data is free for everyone, so it can also be used in other countries. Just to give you an example, the budget for Copernicus for 7 years from 2014 to 20 was 4.3 billion euros, and now they are discussing about the next budget for the next 7 years, and it is in the discussions, it's over 5 billion euros. So it is a huge investment from Europe, and therefore I also think that in Finland we are paying a lot for this. We should also use the data, so that's also part of what I really wanted. So it's kind of we don't want to pay for nothing, we want to also use the data and get the advantage of the huge amount of data. So the services that are developed for the Copernicus program include land monitoring services, marine environment, then atmospheric monitoring service, climate monitoring, and then there is an emergency management service, security services, border surveillance and maritime surveillance, and then there is, in addition, this in situ observation component. So these are services that there is a European Commission is giving some authority, being the prime for developing these services. And the services are using the satellite data. And here are the satellites that are being now implemented to this program. They are called Sentinels, so very nicely Sentinel I, II, III, IV. And then there is something interesting, so there is 5P precursor, and then there is 5 and 6. And already now, 7 satellites have been launched. These are the green ones. The whole program started 20 years ago. It was then called GMES, Global Monitoring of Environment and Security, this Copernicus program. Then I think around 2010, something like that, it changed the name to Copernicus. So 20 years have been built to develop the satellites and the services for that. And now it's entering to the operational phase since 2014-15. And there are, in many of these satellite sets, there are already now 2 satellites, and there will be 2 more in most of them. They are not plotted here, I think, partly because the budget is not clear. Of course, it's quite difficult to think that they would say no, since they have already invested so much, or we have invested so much to the program. But in this picture, not all of the satellites that are planned are given in the picture. So basically, it will provide operational data till 2030 and beyond that in many, many fields. I have a couple of slides of these Sentinels. Now, what are they going to measure? Must say that the atmosphere is my field, so I'm also not too familiar with the other observation types. But I wanted quickly to cover, because I think it's important to really understand the magnitude of this program. So the Sentinel I is a SAR radar, and it will measure with a very nice resolution, even 5-meter resolution, make observations from the surface and provide information. For example, in Finland we're using all of the ice maps during the winter time to guide the icebreakers and winter navigation. Then there is the ships, like in the top picture. The ships can be monitored. Oil spills, for example, can be detected with this instrument. Marine winds, so it measures the roughness of the sea surface, and therefore can be used for marine winds. And then there are for land applications also, forestry, agriculture. And then urban deformation mapping. Also earthquake and volcanic monitoring, like in this picture, to understand during or after the volcanic eruption, how much there has been changes in the land altitudes. And the Sentinel II is a different type of instrument. This is a multispectral instrument, so it measures it with 13 different channels that are targeted for specific purposes. This is really for land applications, so agriculture and forestry, that type of thing, are really using this data. It's using visible wavelengths, and so the pictures what can be obtained with this look something like what we could ourselves also see from the space. Also have some other wavelengths in the shortwave infrared for other purposes. But here is one example. This is a picture that Syke in Finland has developed to analyze also the algae in the west coast of Finland a couple of years ago. It has a 10 to 16 meter resolution, so also quite fine resolution, and it has in satellites there is always the swath, so it means that how wide region this satellite can see at one overcast. So it's 290 kilometers, which means that in 5 days it will cover all the places in the world. So this one, as well as the Sentinel I, they are polar orbiting satellites. So they will fly once every day over each place, or actually twice, but the other one is in night time. And in particular, this satellite is using these visible wavelengths, so in the night it's dark, doesn't see much. Then the Sentinel III, this is for ocean applications, the Sentinel III satellite. It has 3 instruments: radar altimeter, optical imager, and imaging radiometer, and it measures things like sea surface topography and sea temperature, and also then the ocean color, which is linked to chlorophyll, for example, in the sea, ocean areas. Also, I mean, it can be also used for certain applications also on the land. For example, aerosols can be obtained from this instrument as well, but its primary focus is in the oceans. And in this picture there is the sea surface temperature as an example given for this one. So the resolution with this satellite is from 300 meters to 1,600 meters, depending slightly on the instrument. And it will have a rather wide swath, and with the 2 satellites it has basically daily coverage. So every day covers all the whole globe with the observations. Then I just have this one slide showing the atmospheric sentinels, which are more close to the work that I'm doing. And there are Sentinel V precursor. This one is Sentinel V precursor, which was launched last October, 13th of October. And then there is a very similar instrument, the Sentinel V. These are on polar orbit. But then there is this Sentinel IV, which will be put on a geostationary orbit, which means that it will sit on top of the Central Europe, roughly, and measure all the time the Central Europe. Unfortunately, the observations will not really cover well Finland, up to 60 latitude perhaps, but it will provide several observations per day, so perhaps even hourly observations of air quality and atmospheric composition in general, ozone. The Sentinel V precursor and Sentinel V, they will have a daily coverage. And
so is the Sentinel IV then following the Earth?
It is following exactly at the same rotation speed as the Earth. Yes. So these geostationary satellites are very nice for those areas where it can be measured. So unfortunately, high latitudes are not really the focus on them. There is a possibility to have something similar also, but it requires a specific orbit called highly elliptic orbit, where one could have a long time observations from the northern areas. For example, there, these type of satellites, highly elliptic satellites, would provide continuous coverage similar to that one. But it means that the highly elliptic orbit is that the satellite is spending a long time above the North Pole and then go quickly around the South Pole. So 2 of them would be perfect. Something happened. I was talking too much and jumped out of the topic. It's this. Understood. Okay. So the data volumes are huge that are coming now operationally from these missions. So this is simply a picture I wanted to show. These are in terabytes. And here, years 13, 15 here. It was 14 when the first Sentinel satellite was launched, and the violet color here is the Sentinel I and II, and with the blue one here on top is this now the Sentinel III and V precursor. And the data volumes are really, I think, extremely large. So if you have methods to work with big data, so this is there is really a need, which I want to emphasize with this slide. So now I go a little bit to the more details, not much, but a little bit to the indirect observation principle. What do the satellites actually measure, and perhaps then you can think about some ideas where to apply machine learning. So I use the atmospheric observations as an example because these are the ones that are most familiar to me. So the satellites' atmospheric measurements, and many of the other measurements also, are measuring actually scattered solar light. So solar light that is reflected from the surface of the Earth or in the atmosphere back to the satellites. And then gases, aerosols, also the surface, they are kind of leaving their fingerprints on the data. The satellite is these polar orbiting satellites, as I said, they are orbiting the Earth 15 times typically per day, and they are measuring with this swath, which depends on the instrument what is used in these atmospheric observations. Nowadays it's typical to have really wide swath, 2,600 kilometers swath, which covers then the whole globe in one day. And the measurements are made with two-dimensional CCDs where what happens? Okay. Okay, so just saying that, so it measures with the white spot, and then this row there is divided to spatial pixels, and each of these pixels are measured at the same time, and yes, then it depends on the instrument capability, what are the ground resolution pixels. Here is a spectrum measured with that type of an instrument, where this is now from UV wavelengths to near infrared wavelengths, and you see like the spectrum with a red curve, and then the different gases that are absorbed at the certain wavelength regions. So each of these gases, they have their own ways of absorbing the solar light, and from this information then we can calculate how much there is gases in the atmosphere. Here are then from this data what we can get, like maps of nitrogen dioxide, so air pollution, maps, aerosol index, which is also tells about the pollution, aerosols in the atmosphere, dust, and then formaldehyde, heavily related to forest fires, for example, and then sulfur dioxide that is emitted from volcanoes, but also from industry pollution, really nasty pollution at the surface level. So from this spectrum we get nice maps, and this is like tries to explain a little bit what is inside the data processing itself. So we have the observations, like I'm going to look at the satellite data, and then what we need to do, we need to model the observation, how the solar light is coming to the instrument, and the observation, what happens in the atmosphere. So there is a radiative transfer modeling. So we basically model how the signal is coming to the instrument, how much it's scattered, absorbed, and then we need information of the atmospheric profiles, so we need to model them. We need to understand the spectroscopy, how the different gases are affecting the spectrum, and we need, of course, all the geometry information. And then so that is basically what we call then the forward modeling. Of course, then we need to model also the instrument part, so how the instrument is affecting the signal, noise, how the noise is affecting spectral stability, things like that might need to be included in the data processing, instrument function, how it widens the spectrum that we are measuring. And then we have this retrieval algorithm where we put the data and our best knowledge of how it has been obtained into the retrieval algorithm, where then we can make choices. For example, if we need to regularize the solution, how ill-posed it is, we need the fitting algorithm, and we need, of course, the uncertainty quantification and that type of a selection choices. and then we can at the end get then the different gases from the data. So what I think here are many places, for example, where machine learning could be used. The data volumes are huge and we need fast processing of these parts. Perhaps we have some uncertainties in the instrument which might be easier to tackle with some type of automatic methods, approximative methods, or in the radiative transfer parts, or to get rid use of some things that we don't know so well and we don't actually care so much. Just better to somehow neglect them in some sense, in a wise way, clever way. Or then we can perhaps find ways in the retrieval algorithm where we can some. Yes, please ask.
Can I ask which parts of this you would consider solved problems and which are completely unsolved so far?
Basically, we can solve all of the parts for the parameters that we are now retrieving, but there are many things that we could do in a different way, and I think that if we want to make them faster, for example, I mean, now you see the huge amounts of data what we are getting every day, all the time, every second, and actually, I mean, it is, we don't just need to process it once, now the forward stream, but most often we want to reprocess the whole data. We have found some better ways of doing something, so we process everything again and again and again, and it just increases and increases the amounts of value. So I think that speed is something really where there are a lot of cases. I mean, the radiative transfer, but if you do this very carefully, it's really time-consuming. You do it every wavelength separately, basically. And for example, in these there are thousands of wavelengths. And for each picture, I mean. so it's in that sense. I know there are some machine learning methods used, for example, to calculate pollution plume heights, because that's really time-consuming computation. So basically, the time is a driver there. But I think that there are possibilities also to perhaps use multi-pixel methods, where there is more data, and could be some advantages of doing them simultaneously. It's an area which is very little still studied, to use information from several pixels simultaneously or temporally. See the temporal changes, for example. So there were, I had a slide like this, a little bit some ideas what I think, but this might be naive, you might have much better ideas. So faster, more efficient, flexible, adaptive ways. Focus on areas where there is need for more computation. Then approximate things we don't know in the forward modeling or overcome problems in instrument characterization, multi-pixel methods, and the uncertainty quantification. That might be also an area where some type of approximative methods could be used to improve the uncertainty quantification. Then I have a few slides on some examples of the data, air quality data, just to give you some flavor of the observations. So here is a map of nitrogen dioxide air pollution that is emitted from fossil fuel combustion in particular. Traffic is a big source, and it's a short-lived gas, so it stays very close to where it is emitted. So it's very easy to see where it's coming from, already from these type of maps. So this is an average of 2005 measured with this Dutch-Finnish instrument OMI on board the LoRa satellite. It was launched 2004, so we have already now 14 years of data, which is very nice for analyzing changes in the air quality, for example. So here is a picture of 2016, and by comparing these two images, you see nicely what has happened in the world during roughly over 10 years. So in Europe and US, you see that the air quality regulations, they have worked. So the air quality is better. Nitrogen dioxide emissions are clearly lower in Europe, but then on the other hand, you see India is increasing. Middle East is increasing. China is a bit just simply different, I would say, here, compared to these pictures. But if we compare year by year, we see in China that it was increasing the emissions, and then it started to decrease. So now they are on a nice path also in China. So automatic ways to analyze this type of things would be nice. I mean, we can go and study it, place, but there is a lot of data. This is one image now with the recent Sentinel V precursor, which is an excellent instrument. I must say that I still know so how can something be so good with this new air quality observations. We worked a long time with the OMI, and this is like an improved version of that. Much better spatial resolution and much better quality of the data. This is an image of one overpass in India. And you see, it's also nitrogen dioxide. You see there are power plants marked there, and you see clearly the nitrogen dioxide emissions coming from the power plants. You see actually even the wind direction, how it's changing. So you could observe places you didn't know that there is some activities, changes, also linked to other societal things. And then there is something that is very nice also to study with the satellite, is the movement of pollution. Here is the forest fires in Canada or northern US last autumn, I think it was August. Yes, August. And how the air or the ash from the forest fires comes also from Finland. So following this type of pollution. In this case, it didn't affect the air quality. The air we breathe, it was higher in the atmosphere, and that's why it was transported so long way. So desert dust is something that also every now and then, perhaps you remember that one day when suddenly the sun was so red, so it was a Saharan dust that came to Finland. Poland is also traveling with the winds, sulfur dioxide and ash from volcanic eruptions. It goes higher to the atmosphere and then can be transported long ways. And here is this is really our example. This is a service that we are running at Finnish Meteorological Institute. We are receiving the data directly from the OMI instrument at Sodankylä, and we process the data quickly there within 15 minutes after the satellite overpass and put it to the web. Everybody can have a look, and this was the case on the Grimsvötn volcanic eruption in 2011. And there are two pictures. On the left one, there is sulfur dioxide from the volcano. You see there, red curve, and then the other one is the ash. Same day, but you see quite different pictures. So the volcanoes, they are emitting different things, and it goes to different altitudes, and the winds are in different directions, so they can actually take really different routes, these plumes. So this one goes more to south, and that one goes more to northward. So it's easy when you really know what you are doing and when you have a lot of experience, but of course if you are, this is the first time you see this type of images, so how do you know what is real signal or what is just artifacts in the images? So there is noise and other nasty things that you have to get rid of. We look at this more often. We know perhaps what to look at, but if we want to develop services, alerts, for example, we need methods to analyze this type of data also and get rid of the facts that are not relevant. So there I also think that perhaps some automatic methods could be developed. Better methods that exist at the moment. So these were just some ideas I thought that could be linked. Automatic alerts, analysis, classification of cases, plume detection, or source identification. And then this noise reduction takes on post-processing. And then I have some topics on the data fusion. This is just a slide. But this is actually what I think that could be the most powerful or most potential ideas. So in general, just make further analysis, use different datasets, put them together, either satellite datasets or some other datasets. Analyze things that are going on local or regional or global ways or temporal analysis. And in particular, I think that there is a huge potential really to combine all these, if you think about all these Copernicus datasets on different things with other data sources, health data or sociological or economical data together. I mean, of course, it requires typically some time series to have enough data, but now is perhaps the right time to start thinking about it. There will be this type of data till 2030s, etc. To think about all the other applications where this global data could be combined. So I really think that the data volumes are so huge that we are not going to have very I mean, we need some really automated, and I think the machine learning can be there very helpful to think about dependencies or really getting new information from that data sources. So I think just imagination is the limit there. And this is then to advertise that we are going to have a hackathon at the Finnish Meteorological Institute in a couple of weeks, 16th to 18th November. It is organized together with the European Centre for Medium Range Weather Forecast, so the largest weather forecast, or the joint European weather forecast organization, and then the EUMETSAT, European Meteorological Satellite Organization, and Finnish Meteorological Institute. University of Helsinki is also participating. So it's from Friday to Sunday at FMI. And the deadline is a couple of days from now. Perhaps you can distribute the information. It will be on atmospheric stuff. So, on my summary slide then. So I think the EU is putting a huge effort on developing this Copernicus satellite program, and there will be a huge number of observations. There will be more satellites in the future. They are considering about expanding the series of satellites. For example, quite seriously now thinking also implementation of carbon dioxide monitoring mission, in particular to measure anthropogenic emissions of carbon dioxide, which is really the main cause of the climate change. And the huge data volumes call for efficient data processing methods. I think in all levels, from the beginning, but also when using the data, combining with other data sources. And as I said, I really think that the idea of combining it with other data sources is something really interesting. So, thanks.
We have a couple of minutes time for questions. Please.
Yes. So you mentioned the NASA data for example, the US data, or so Europe is very keen on sharing their data, but how about the other countries that are?
US has always been very open with their data. So all these atmospheric data, for example, it has always been very free, and they are very efficient also in distributing the data. And yeah.
What about China? Where is it?
Yeah, that's difficult. We collaborate with China, so we have a joint project. They have launched their first carbon dioxide satellites, and but it's difficult to get the data from there. So that's really our main motivation behind the collaboration, to try to ensure that the data is also shared. Yes. But of course, the satellites, each of the satellites will cover the whole. I mean, of course, there are regions which there are some specific difficulties, but they are not because of the political things, but some other reasons. Yes.
You emphasize the amount of computation being a bottleneck. So, is it which part is the biggest bottleneck? Is it computing the forward model?
Yes, typically the forward model. Yes.
And it's done based on the first principles on how the race can
I mean, there are different solutions. And some are, of course, principles very slow, then there are some approximations and even more approximations. So there is quite a big variety of methods being developed on that. But I think there is still a lot of potential to improve things.
Okay, time for one short question.
Yes, so I think this is very interesting, this combining this satellite observation with some other data, ground-based observations. So my question is, have you already done something like this and maybe used some machine learning methods?
Personally, I don't really have a lot of experience. We made it was a student made years ago, basically cloud screening, or combining cloud screening with another type of observation. So, because in many of the instruments, clouds are nasty features, and we want to be absolutely sure where there are no clouds. So it was more like that type of application. I mean, not much.
Okay, let's thank the speaker.